There is a period in the universe's history when the lights were, quite literally, off. Not dark like nighttime. Dark like nothing anywhere was making its own light yet. The universe had already done the thing everyone pictures when they think Big Bang. It had cooled enough, about 380,000 years in, for electrons and protons to finally combine into neutral atoms, releasing a flash of light that's still visible today as the cosmic microwave background. Footnote 1. That happened. That part everyone's seen the picture of. And then, for the next 100 million years or so, nothing else did. No stars. No galaxies. No structure at all, really, just a thin, cooling fog of hydrogen and helium, drifting through an expanding universe, doing absolutely nothing interesting for longer than it took multicellular life to go from first slime to you. Astronomers call this stretch the cosmic dark ages, and it is exactly as anticlimactic as it sounds, right up until it very much isn't. Because eventually, somewhere in that fog, gravity found its first foothold, and what came out the other side wasn't a star like our sun. It was something bigger, hotter, faster, and stranger than almost anything that exists in the universe today. Something that burns so violently it barely got to exist at all. This is the story of the first stars. We've never seen one. We might be starting to. Here's what the universe was actually made of during those 100 million plus dark years, and why that composition is the whole reason the darkness lasted as long as it did. After recombination, the moment electrons and protons paired up into neutral atoms, the universe's contents were about 92% hydrogen and 8% helium by atom count, with only the faintest trace of lithium mixed in. Footnote 2. That's it. That's the entire periodic table available to the young universe. 3 elements and only the very lightest of those. Everything heavier, carbon, oxygen, iron, every element this channel has spent time on in the periodic table has a crime scene. Didn't exist anywhere yet. Stars hadn't forged it because stars hadn't formed. I am attempting to imagine a universe with only 3 elements available to it. I find the exercise more unsettling than I expected. Perhaps because I already know how it ends. That absence of heavier elements, what astronomers with characteristic bluntness call metals. Everything past helium counts as a metal in this context, which will never stop being funny, isn't just a trivia fact. It's the actual mechanism that kept the dark ages dark for so long. Here's why. When a cloud of gas starts to collapse under its own gravity, on its way to becoming a star, it needs to shed heat to keep collapsing. Compress a gas and it heats up, that's basic thermodynamics, and if it can't cool back down, the rising pressure eventually pushes back hard enough to halt the collapse. Modern star-forming clouds cool efficiently, because they're full of dust and metal-enriched molecules that radiate heat away easily, letting a cloud fragment into many modest, sun-sized pieces, which is why a nebula today can produce thousands of ordinary stars at once. Footnote 3. The primordial gas had none of that. No dust, no metals, nothing but hydrogen and helium, chemically about the worst possible cooling agents available. The only cooling channel open to it was molecular hydrogen, H2, and it's a slow, inefficient one. Footnote 4. Slow cooling means the cloud can't fragment the way modern clouds do. Instead of splintering into a few thousand sun-sized clumps, a primordial cloud tends to collapse as one enormous, coherent mass, because nothing was cooling it fast enough to break it apart first. That single difference in cooling efficiency is the reason the very first stars in the universe weren't going to be anything like our sun. The universe wasn't randomly deciding to make giant stars first. Compared to today's chemically rich star-forming regions, it barely had a choice. Run that cooling problem forward to its conclusion, and you get what astronomers call population 3 stars, and stars might be underselling it. Simulations consistently point to primordial stars forming with masses in the range of tens to several hundred times the mass of our sun, with some models suggesting stars exceeding 1,000 solar masses were plausible in the right conditions. Footnote 5. For comparison, the most massive stars known to exist today top out somewhere around 200 solar masses, and those are considered freakishly large outliers even now, in a universe with every cooling advantage the early universe lacked. Footnote 6. Mass like that comes at a cost, and the cost is time. Stellar lifespan runs inversely to mass. Bigger stars burn through their fuel dramatically faster, not slower, because gravity forces a much higher fusion rate to hold up against their own weight. Our sun will burn steadily for roughly 10 billion years. A star at even 100 solar masses might last only 2 or 3 million. Footnote 7. At the extreme end of the population 3 mass range, some models suggest lifespans measured in the hundreds of thousands of years. A cosmic eye blink, over before the light from the star's own birth had finished crossing its host galaxy. These stars would also have been almost unimaginably luminous and hot. Surface temperatures potentially exceeding 100,000 Kelvin, compared to the Sun's roughly 5,800, pumping out intensely ultraviolet heavy radiation. Footnote 8. That radiation output matters for reasons well beyond any individual star. Population 3 stars are widely considered the leading candidate for kickstarting cosmic reionization, the process by which the neutral hydrogen fog that filled the Dark Ages got stripped back into ionized plasma, clearing the way for the universe to become transparent to light the way it is today. Footnote 9. So here's the shape of the whole story: stars that were bigger than almost anything since, brighter than almost anything since, and gone faster than almost anything since. And in the process, they may have single-handedly flipped the switch that ended the universe's dark ages. Extraordinary stars, doing extraordinary work on a schedule too short for the universe to have caught more than a glimpse. Which raises the obvious problem. If they burned out that fast, that long ago, how would anyone ever actually find one? It is incredibly fascinating that we are attempting to detect an object that no longer exists, using light that has taken longer to arrive than the current age of most galaxies we can see. The logical response to this difficulty is not to abandon the search. It is to stop looking for the star and start looking for its consequences. Since no population 3 star has ever been directly, unambiguously observed, astronomers have built an entire toolkit of indirect evidence instead, proxies that a pop 3 star could plausibly have left behind, even though the star itself is long gone. The first proxy is death, specifically a very particular kind of death. Stars in a narrow mass range, roughly 140 to 260 solar masses, are predicted to end not in an ordinary supernova, but in what's called a parinstability supernova, a catastrophic explosion driven by high-energy gamma rays converting into particle-antiparticle pairs deep in the star's core, abruptly dropping the internal pressure holding the star up and triggering a runaway thermonuclear explosion that leaves nothing behind at all. No neutron star, no black hole, just a rapidly expanding cloud of matter and a very specific chemical fingerprint in the elements it forges and scatters on its way out. Footnote 10. Find that fingerprint in a galaxy old enough, and you've found indirect evidence a population 3 star was there. The second proxy is even more ingenious. Don't look for the star. Look for its grandchildren. A small number of extremely metal-poor stars have been discovered in the Milky Way's halo, stars so chemically pristine that some, like SMSIS J0313-6708, discovered in 2014, show no detectable iron at all in their spectra, setting a still-standing record for the most metal-poor star ever found. Footnote 11. These aren't population 3 stars themselves, they're too old and too metal-poor for that particular framing to make sense, but not quite metal-free. They're thought to be second-generation stars formed from gas that had been enriched by exactly one previous generation of population 3 supernovae, and then never got polluted further. Read their chemistry carefully enough, and you're reading a fossil record of the exact explosion that seeded them, a chemical echo of a star nobody ever directly saw, sitting quietly in our own galactic backyard the entire time. Between the corpses, parinstability signatures, and the fossils, extremely metal-poor stars, astronomers have built a genuinely compelling circumstantial case that population 3 stars existed roughly as theory predicts. What neither approach has ever delivered is the thing everyone actually wants: a direct, unambiguous look at one of these stars, alive, doing what it did. That's where this story gets current. JWST gets used 2 very different ways on this channel. Later we'll point it at a nearby planet's atmosphere, looking for a sign that something's alive right now. Right here we're pointing it the other direction entirely, past every planet, past every galaxy we can name, trying to catch the flicker of the very first stars that ever turned on. As of this year, the search has produced its most serious candidates yet, and the honest answer about all of them is compelling, contested, and not yet settled. The strongest current case comes from a source sitting just 3,000 parsecs from GNZ 11, one of the most distant known galaxies, at redshift 10.6, meaning we're seeing it as it existed when the universe was roughly 440 million years old. In April 2026, A team led by Roberto Maiolino confirmed, using high-resolution JWST spectroscopy, a helium-2 emission line at that location with no detectable metal lines whatsoever, cross-confirmed by an independent hydrogen gamma detection from a separate research group. Footnote 12. Helium-2 emission this strong, entirely unaccompanied by any metal signature, is difficult to produce through any mechanism other than the extremely hot, hard radiation a cluster of population 3 stars would put out. The team's own conclusion was direct. They found no satisfactory alternative explanation from any other known class of object. That's about as strong as this field currently gets, and it still isn't a confirmed detection in the way a fingerprint or a DNA match would be. It's the best supported candidate interpretation of an observation that a genuinely primordial star population is the most plausible explanation for. It's not alone. In late 2025, JWST observations of a gravitationally lensed galaxy called LAP 1b, seen as it existed roughly 800 million years after the Big Bang, produced another strong population 3 candidate signature, using natural gravitational magnification to catch light that would otherwise be far too faint. Footnote 13. And further back in the search's history, a lensed object called Earendel, at redshift 6.2, the most distant individual star candidate ever identified, was proposed as a possible population 3 star in 2022, though its case remains genuinely ambiguous. It hasn't shown the lensing-driven brightness variability that would help confirm its nature, and a purely population 3 interpretation is still only one live possibility among several. Footnote 14. Here's the honest caveat the whole field carries, and it's worth stating plainly rather than letting the exciting parts speak for themselves. Every one of these candidate detections has to be weighed against alternative explanations that can mimic parts of the same signal, active supermassive black holes, or gas ionized by early direct collapse black holes forming through entirely different physics. Footnote 15. Researchers actively working this problem in 2026 describe the landscape as one of genuine progress paired with genuine ambiguity, multiple increasingly compelling candidates, and no fully settled confirmation yet. So where does that leave things honestly? Closer than we've ever been. Not there yet. And that, itself, is a genuinely interesting place for this story to sit. Worth separating explicitly what's actually solid here from what's still an open question, because this episode has been carrying both at once, and they don't deserve equal certainty. Solidly confirmed, resting on decades of independently cross-checked physics. The composition of the early universe, roughly 92% hydrogen, 8% helium, trace lithium, from Big Bang nucleosynthesis. Footnote 16. The basic thermodynamics of gravitational collapse and the cooling efficiency gap between metal-free and metal-enriched gas. Footnote 17. And the theoretical mass range and short lifespans predicted for population 3 stars, which rest on stellar physics that's been tested extensively against stars we actually can observe. Genuinely still open, whether any specific JWST observation to date, GNZ11's HII emitter LAP 1b Earendel or any candidate still to come, represents an actual, confirmed detection of a population 3 star, rather than a well-disguised imposter. That's not a minor asterisk. It's the entire question this section of astronomy is currently built around answering, and as of 2026, it remains formally unresolved. If we are looking for a star that died before most of the elements in your body existed, we are looking at it using light that left before the light had anywhere else to go. And we are reasonably confident we might have almost maybe found one. Science everybody. There's a fitting handoff buried in that uncertainty, and it's one this channel has already half told. Back in The Periodic Table Has a Crime Scene, this channel built out where the heavier elements in your own body actually came from, ordinary stellar fusion for most of it, 100 seconds of colliding dead stars for a smaller, stranger fraction. Every single one of those elements had to start somewhere. Population 3 stars, whether or not we've caught one directly yet, are the leading candidate for the very first furnace any of that fusion ever happened in, the stars whose deaths seeded the first metals the universe ever had, the raw material every subsequent generation of star, planet, and person eventually got built from. We may not have a confirmed photograph of the first stars yet. We're already pretty sure we're made in part from what they left behind. Next, this channel follows that leftover material somewhere much more specific. Not the universe in general, but the exact clump of it that became our own solar system, and the surprisingly violent process it went through on the way to becoming rock, gas, and eventually us. Here's the thing about the first stars. They didn't last, they didn't get named, and as of this year, we still can't say for certain we've actually seen one. And none of that makes them a footnote. They burned violently, briefly, in a universe that had nothing else going on yet, and in doing so, they may have ended the darkest stretch the cosmos ever sat through, and started handing out the raw material every star, planet, and person after them would eventually be built from. Not because they were trying to. Because that's just what a few 100 million years of unglamorous physics adds up to, when nobody's watching and nothing's keeping score. It's worth sitting with the next clear night you're outside. Whatever star you're actually looking at, it's not the first one. But somewhere, a long time before that light even started its trip toward you, something was. There's still a lot of universe left to look at,